Bismillahirrahmanirrahim. My name is Mujtaba Hassan and I am a PhD student at Tsinghua University, Beijing, China. And today my presentation topic is temperature and precipitation climatology assessment over South Asia using the regional climate model called as ECHAM4.3, which is the basically evaluation of the model performance. The outline of presentation contains introduction, material and methods, results, and some conclusions. As we know that today climate is much more complex issue than as it was before the Industrial Revolution. And it has potential impacts on health, agriculture, food, water resources, etc. So, in order to understand the nature and extent and the magnitude of these climate changes, usually we used global circulation models. But the problem with the global circulation model is that they cannot resolve they have a low resolution, they have a coarse resolution, and they cannot resolve the topography, land use, and cloud feature at the regional scale. So that's why we need downscaling, and using downscaling techniques, we can obtain the high resolution climate and climate change information from comparatively coarse resolution global circulation models. In order to analyze the climate change impact assessment studies, we use two types of downscaling techniques. First is the dynamic downscaling and second is the statistical downscaling. Both have some advantages and disadvantages. The advantages of dynamic downscaling is much more as compared to the statistical downscaling, because dynamic downscaling is much more consistent, physically consistent and reliable, and can resolve the local features and can also have a good effects to include the convective precipitation especially. In case of statistical downscaling, we use some statistical relationships between the GCM's output and local climate statistics. In dynamic downscaling, we use regional climate models. The regional climate model are used for the regional climate processes, regional climate change impact studies, and also for seasonal climate variability. The basics of the regional climate model are same as that of the numerical weather prediction models, except that the regional climate models run for a longer period of time. In case of the nested regional climate models, we usually provide the initial and lateral boundary conditions to RCM from the GCM or reanalysis of observation. This is the topographical map of the study area of South Asia from 50 degrees to 100 degrees east and 5 degree north to 40 degree north. It is further divided into sub-regions like Bay of Bengal, Western Ghats, Central India, Northern Pakistan and India, and Southern Pakistan. The topography of the domain is complex as shown in the figure, which have high mountain ranges of the Hindu Kush, Karakoram and Himalaya ranges, and have a different types of weathers that pose a great challenge to the climate model in order to reproducing the observed climatology. Here is the short introduction of the regional climate model. In this study, we use the International Center for Theoretical Physics regional climate model version 4.3. Initially, the first version was evolved in 1989 by Dixon et al. In 1989, and then it go through for the further development, and finally we have its fourth version that is introduced by the Georgia et al. In 2012. Some important feature of the regional climate model: it has a dynamic structure, and they have a hydrostatic version of the mesoscale model version 5 of the National Center for Atmospheric Research and Pennsylvania State University. It has two type of land surface schemes. One is the biosphere atmosphere transfer scheme, by Dickinson et al. And second is the community land model version 3.5. The radiation package in the regional climate model contain NCORS global community climate model version 3. Resolve scale precipitation contain the sub-grid explicit moisture parameterization scheme, and the cloud radiation part contain in 3 parameters like cloud fraction cover, cloud liquid water contents, and cloud effective droplet radius. Planetary boundary layer scheme based on the diffusion relaxation concept of Holtzlake. The most important part, as every regional climate model have, this regional climate model ECHAM4.3 have also a sensitive and important part, which is the convective precipitation, which is also called as the physical parameterization of the model. And mostly the evaluation of the model is based on this scheme. Currently, we have a different option of the convective parameterization scheme. In the present study, we use the MIT manual scheme. In experimental design, we conducted 2 experiments. In first experiment, we used the initial and lateral boundary condition. In first case, we used the initial and lateral boundary condition from European Center for Medium Range Weather Forecast 40-year reanalysis data called as ERA40, and the experiment which we conducted named as ECHAM ERA40. In the second experiment, we use European Community-Hamburg atmospheric general circulation model ECHAM5, and the experiment called as ECHAM5. Sea surface temperature is prescribed from the global ice and sea surface temperature. Model topography and land use data are obtained from the global land cover characterization. Horizontal resolution of the regional climate model ECHAM4.3 is taken as the 50 kilometer, and the total number of vertical levels are 18 sigma level with 5 hectopascal at the top of the model. Here is the input name list of the model that contain different stanzas. Just few parameter I want to explain. This is the domain, horizontal resolution, ds is equals to 50 kilometer that, and second is the boundary condition. Usually we provide the initial and lateral boundary condition from GCM or reanalysis 6 hour daily, and sea surface temperature, as I told in earlier in the slide before, is GISST, global ice coverage sea surface temperature, and the two driving fields, that is ECHAM5 and ERA40, are used in this study from 1971 to 2000. And this is the important part of the model, which is called as the physical parameterization scheme of the model, that has a relaxation exponential techniques and planetary boundary layer. Cumulus convective scheme is MIT manual, as I told earlier. And the scenario that we used in this study is the for current simulation, means in order to evaluate the model before going to the climate change impact assessment, it is important first to analyze the ability of the model to reproduce the observed climatology. So we use reference period from 1971 to 2000. Here are some results. In the case of results, we use 2 kind of observational data set. That one is the CRU Climate Research Unit UK, University of East Anglia, and second is the UDEL, University of Delaware observation data set. These 2 are the observational data set, while ERA40 and ECHAM5 are the driving field, 2 driving field, and these are the 2 experiments called as ECHAM4 ERA40 and ECHAM4 ECHAM5. Left panel show the winter season, and the right panel show the summer season. In order to analyze the ability of a model in a detail, we calculate the biases in the model. These are the spatial distribution of the temperature biases for winter season. In this figure, we can see that second line, that is contains C, D, E and F. Sorry. Yeah. It's not working well.
Press the front button. Front button.
It's not working. Okay. Okay. Here is the ERA40 minus CRU biases. ERA40, as I explained, that it is the reanalysis data set. And in second case, we have a ECHAM5 GCM minus CRU. And here are the simulation, two simulation. One is from ERA40 driving field, and second is from ECHAM5 GCM. In these two cases, we can observe we have some biases over the northern part of the domain. I mean, the northern India and Pakistan. We have a cold bias up to -6 degrees centigrade, and here over the central India we have a warm bias up to 4 degrees centigrade. If we compare these two figures, although ECHAM4 ERA40 minus CRU have some biases, but the cold bias over the foothills of the Hindu Kush Himalaya region has been reduced effectively. Similarly, in this case, the spatial distribution of temperature bias also reduced after downscaling from ECHAM5. ECHAM5 minus CRU have a more cold bias, and this bias is reduced here. Similarly, warm bias is also reduced in this case. The next is the summer season of reanalysis, GCM, and the two simulations. In this comparison, we have a cold bias that is much more as compared to observational data set. But in case of the ECHAM5 and ECHAM ECHAM5, this warm bias is reduced here. In case of precipitation, again we use two observational data sets, CRU and UDEL, and two driving field and two simulations. Left panel show the winter season, and right panel show the summer season. If we see the ERA40 purely simulate the seasonal mean climatology for precipitation and is mostly drier over the whole domain. While in case of the two simulation, we have some more excessive precipitation over the northern part of the domain. Again, we analyze some biases, and in journal we can see that we have some wet biases over the northern part of the domain. And finally, in the summer season, that is June, July, August, again we can see we have some biases, but these biases are reduced in the two simulations. Finally, we calculate the annual cycle for 1971 to 2000, and we take the average of the annual cycle for three regions, that is Bay of Bengal, Western Ghat, and northern Pakistan and India. We choose these regions because of our future studies, which would be the continuation of this study, because we want to analyze the impact of climate change because of these regional climate simulations. So we have most severe weathers, more precipitation in summer season because of the monsoon season, and the monsoon season arises from Bay of Bengal and Western Ghats and affect the northern part of the domain. So in case of temperature, we have much more better results in case of the monthly area average temperature as of the two simulation as compared to the observational as compared to driving field. But in case of precipitation, we have some mixed result of dry and wet precipitation seasons. For example, as I explained in earlier slides, that the model tend to overestimate the precipitation over the northern part of the India and try to overestimate northern India And finally, we conclude that these biases, the biases that we saw in the graphs, have some different reasons. The reason is that these biases may be inherited from the GCM or reanalysis data. Second is that the domain, because of the choice of the domain, because the domain has a complex topography. And the third may be because of the internal dynamic of the model, because model tried to develop its own climatology. However, in general, if we conclude, we can say that the main characteristics of the precipitation and temperature are reproduced well as compared to the driving field. And downscaling, dynamic downscaling has improved the output of the reanalysis and GCM in many parts of the domain. However, because of these biases, the further investigation is required in case of the physical parameterization and land surface schemes of the model. And as a result of this analysis of our simulations, 30 years present day simulation, we run the model for further simulations to check the other land surface and convective precipitation schemes. And hopefully in future we will present some more better results. And then we will use these results for future climate simulation by using the latest RCP scenarios. And finally, we will use the output of the regional climate model to the hydrological model for hydrological simulations. Thank you.
Thank you, Dr. Hassan, for this very informative and excellent presentation. We have a couple of minutes for questions, maybe 2-3 questions. I know that many of you are working on climate modeling, so we expect many questions.
Hi, I just have one quick question. Sorry. Oh, I'm sorry. I don't know too much about this climate model, but I write weather generators. I know that temperature and percep data is highly dependent on the regional characteristics. So I was wondering, how do you incorporate that kind of difference between regions in that climate model?
Can you repeat your question?
So what is your resolution for that?
Resolution
model?
is 50 kilometer. Horizontal resolution is 50 kilometer.
I was wondering if you expect a lot of difference, or what kind of parameter you use to distinguish the temperature and precipitation data between different regions?
Actually, in case, I think you are talking about the statistical weather generators. In regional climate models, we use the driving field. Driving field means the reanalysis data or the GCM. In case of topography and sea surface temperatures, if we talk about the temperature of the region, we provide the global sea surface temperature, as explained, GISST, global ice and sea surface temperature, at 10-minute resolution. While in case of precipitation, we get the data from the reanalysis or GCM and provide to the regional climate model. And regional climate model, according to the domain and the resolution of that is selected in the input name list, develop its own climatology for that region. And then it give the results.
All right, thanks.
Do you think that 50 kilometers is enough? I'm thinking that the mountains, maybe you have in those 50 kilometers, you have maybe the Everest and other,
You mean?
Do you think maybe it's too big, for assessments of climate change?
You are talking about the domain or the resolution?
The resolution of the downscale.
Actually, the resolution is 50 kilometer is enough, because the regional climate, this model has a hydrostatic version, and the hydrostatic version of the model cannot allow the resolution below the 20 kilometer, and 50 kilometer is is enough, I think, because in some cases, if we want to run the model below the 50 kilometer, but it has a problem because of the domain.
Okay.
One more question.
Microphone.
Okay, I think this is very interesting. In case of, well, I'll take example Nepal. I think with respect to his query, the elevation varies quite abruptly, okay? Within the 120 kilometer span, from south to the north, elevation vary from 100 meter to, well, 8,848 meters. How can we apply this regional model in case of Nepal,
Actually,
where the elevation and temperature vary so quickly, and also there were precipitation?
Actually, only for Nepal we cannot apply this model. We have a large enough domain for the regional climate model to develop its own climatology. So if I want to consider, for example, Pakistan, I cannot just include Pakistan, because the system that are affecting Pakistan are coming from Mediterranean Sea and also from the Bay of Bengal and Western Ghats, like Indian Ocean. And similarly, it has effect of the domain along the, as he told, that foothills of the Himalaya region. So this is a big task for the climate models, climate scientists, to actually every regional climate model have every physical parameterization scheme have a different effect over the different region. The task of the climate scientist is to check which one is the best and then tune the model for the best scheme. So still we are working, scientists are working over this problem of the domain selection, and it cannot be easily selected. We should conduct some initial experiment, test experiment, in order to check which one scheme is most better for the region. So for your question, if you just consider Nepal, it is not possible. We should have to consider the domain large enough. Even this domain is small. Usually in most of you may know about the Cortex domains, coordinated regional climate experiments. They have a large enough domain. This is a small domain. So the selection of domain is also have a great influence on the results.
Thank you.
Thank you.
Thank you.